Okay, so I'm making a solid state Tesla coil, so I thought it'd be fun just to talk about what I'm developing and keep some progression videos. If you want a more detailed overview of everything I'm talking about, things like schematics or very nuanced specifics of each component, I have a GitHub, so I can link to that. So here I'm just going to be talking about the interrupter circuit that I've built, and in the end I might divulge into other stuff. But so this is an interrupter, so this is going to be controlling the spark output in terms of frequency and size of the spark, and it does that by controlling the transistors that are used for an inverter circuit, which is going to be sending the signal through the primary coil that resonates with the secondary coil. But focusing on the interrupter circuit, so it's a 2 555 timers together, one in astable and then the right one here in monostable, and together it's going to enable me to have a duty cycle, an adjustable duty cycle. So quick overview of how everything works. Red LED just tells me the circuit is drawing power. I'm eventually going to have other stuff here, so if this breaks, the blue LED is going to go off, and I may not know that the circuit is drawing power, so that's the purpose of red LED. Blue LED is giving me a visual signal of what the output waveform is like, mainly for aesthetic purposes, but here's the output waveform on my scope, and the blue LED is doing the same thing. So yeah, here specifics, we got 555 timer in astable mode. So what that means is, astable. And what that means is with this potentiometer, I can adjust the frequency of the signal it sends out. So to give you reference, I'm turning the potentiometer, and you can see that the frequency of the signal adjusts. And I've got it tuned so I can go from around 30 or 40 hertz that you see in the top right corner of the scope, all the way to around 180, 170, something like that, 175, yeah. So that signal output is then fed into this monostable 555, and the monostable uses each one of these initial pulses, and that tells it to start producing a signal, and then the rest of the circuitry dictates how long that signal is going to be sustained for. So this 555 timer circuit is just controlling this bit right there, the on time. And you can see if I adjust the other potentiometer, you can see I'm now changing the width, the on time of the circuit. So together, I can now change the frequency, change the width. So complete duty cycle control, which is always nice. Eventually, because 555 timers, I find them pretty finicky. I'm just not very familiar with using them, so I'm still pretty bad at getting all the calculations exactly as I want them. And ideally, I'd want around 0 to 250 hertz, and I wouldn't want to exceed something like a 15% duty cycle instead of 20%. 20% is kind of pushing the limits. And I think eventually I'm just going to replace all this with something like an AT-Tiny that's programmed to have an adjustable waveform using potentiometers instead of all this circuit stuff. And then looking even further down the line, for if you have ever wondered how people make musical Tesla coils, essentially audio signals look exactly like this through the air, and a higher pitched sound is going to have a higher frequency, a lower pitched sound is going to have a lower frequency. And then for musical Tesla coils, when you're playing the piano or something, they're just converting the notes using a simple equation to a waveform. So it's quite simple to take a non-musical Tesla coil and make it musical. There isn't much adjustment. It's primarily just the circuit. So yeah, that's what we've got going on here. Just to show off some cool things, something that I didn't really realize until I started working with electronics was how LEDs and lights in general, I think most incandescent light bulbs, don't quote me on that, I might be wrong, but the brightness of them isn't actually power or voltage or current or anything. It's just the frequency of the signal being pushed through them, because you can see that this is a broken up signal. It's not a continuous stream of voltage running through the LED, but it appears to be on. However, if I lower the frequency, if I lowered it enough, it looks like it's blinking. There is some screwiness with the 32 frames per second that the phone I'm recording with is picking up. So even when I increase the frequency, all of a sudden it's gonna look kind of weird. Yeah, like right now it kind of looks like it's pulsing. So, but yeah, I just thought that was interesting that LEDs, when they look on, they're not actually on. It's just they're pulsing, unless it's like this. But for power purposes, if you're trying to save power, you know, why supply constant voltage when, you know, having a duty cycle of 20% here, I could only supply 20% of what a constant voltage would have otherwise been, so I save 80% of power, you know? Yeah, so anyways, that's the interrupter circuit. Just get an aerial view in case anyone's interested. Hands are creating shadows, there we go. And yeah, thank you for watching.